Okay, we are at section 34.2, the ray approximation and ray optics. It's only short uh, two slides, so let's share the PowerPoint. Now, if you were to have a point source of light, you could almost think of it as the positive charge. When we studied charges, all you have these rays emitting out from uh, the positive charge. But at a distance, those electric field lines emitting from a positive charge become, we assume them to be parallel when the distance is far. Well, it's the same thing here. You can think of a point source of light, and light emanates from all directions. But as you get far from the source, the light source, you can consider the rays parallel, and the wave fronts, uh, perpendicular to the rays. They're parallel to each other. There are these wave fronts going. Let's read the box. The rays, which always point in the direction of the wave propagation, are straight lines perpendicular to the wave fronts. So again, this is a for the conditions where you're far away from the source of light. Now, if you when you have waves and wave fronts coming at an opening, and the opening, let's say you have a small hole in the opening, but the diameter of the hole is much larger than the wavelength of the light source. When let's see, did I say that right? The diameter is much larger than the wavelength. When the wavelength is much smaller than the diameter, the rays continue in a straight line, and the ray approximation remains valid. So you can imagine a piece of cardboard and a flashlight. You have a hole in the cardboard. You shine a flashlight, and sure enough, you'll see the shadow of the cardboard, but you'll see a little spot on the wall where the light is coming through. Now, when lambda is approximately, when the wavelength is approximately open to the diameter, the rays spread out after passing through the opening. This is a phenomenon called diffraction, and we'll study that in later uh, chapters. And when lambda is much smaller than I'm sorry, when lambda is much greater than the D, the opening behaves as a point source emitting spherical waves. So we have the two conditions. Lambda is much less than the diameter of the hole. Lambda is approximately equal to the diameter, and then lambda is much greater than the diameter. And the one we're going to concern ourselves with for the study in this chapter is case A, where lambda is much smaller than any diameter. This works, so this will work for mirrors and lenses and things like that. Later on, we'll get to diffraction. And I believe that's it for this section. Yes, the next is waves under reflection. So we'll stop it here. Just a short little 2-slide lecture.